and welcome everyone to one more lecture of probability and statistics. Today we will try to find out moment generating functions for different probability distribution. First of all, as we know, moment generating function is denoted by Mth302 and equals to expectation of Etx, e raised to power tx. Now, as we know, for discrete, if we want to find out expectation of Etx, this will be equal to summation x Etx times f of x, where f of x is probability distribution function for random variable x. Now, first we will find out MGF for Poisson distribution. As we know, formula for Poisson distribution is P x semicolon lambda equals to e raised to power minus lambda, lambda raised to power x by x factorial. Now, mxt will be equal to, as we know, this is a discrete probability distribution, so this will be equal to summation x equal to 0 to infinity, because Poisson random variable only take non-negative values 0 to infinity, Etx into e minus lambda, lambda raised to power x by x factorial. So this will be equal to e minus lambda is a constant. We can take this outside of summation. Summation x equals to 0 to infinity e t into lambda whole raised to power x by x factorial. Now, if we will expand the x summation, so this will be e t lambda x, x will be 0, so this will be 1 by 0 factorial, that will also be 1. 1 plus e t lambda by 1 plus e t lambda square by 2 factorial, e t lambda by 3 by 3 factorial, so on. Have we seen this somewhere? As we know, expectation of x, e raised to power x is equal to 1 plus x by 1 factorial, x square by 2 factorial, x cube by 3 factorial, and so on. So, if we replace x with et lambda, so this will be equal to this expansion. So, this will be equal to e minus lambda times e t lambda, e raised to power e t lambda. This is our moment generating function for Poisson distribution. Now we will try to find out mean of Poisson distribution using this, so we can prove that this is correct MGF to cross check. So first we know e of x equals to mean, and this equals to moment generating function's first derivative, and by putting value of t equal to 0, and we already know that mean for Poisson distribution is lambda, and also variance equals to mean equals to lambda for Poisson distribution. So first derivative of m dash, m dash will be equal to, this is a constant e, so this will be e minus lambda e raised to power 8t lambda into e raised to power t lambda into t's differentiation derivative, this will be 1. So this is first derivative of moment generating function. If we will put value of t equals to 0, so this will be e minus lambda into e raised to power 0 into e raised to power 0 into lambda into 1. Now e raised to power 0 into lambda. So this will be e minus lambda into e plus lambda into lambda, because e raised to power 0 is 1. So this will be equal to lambda. So this is our mean, and hence we can say that this is our correct moment generating function. Next we will find out moment generating function for negative binomial distribution. First of all, we know that probability function for binomial distribution, negative binomial distribution, is b asterisk x semicolon k comma p equals to x minus 1 c k minus 1 p raised to power k q raised to power x minus k. Now we know that moment generating function is denoted by mxt, and this equals to expectation of ext, and in this case this will be equal to summation. Now our value, our x is fixed. Let's take our k is fixed and x is variable. So this will be summation ext x minus 1 c k minus 1 p raised to power k q raised to power x minus k. Now we can write q raised to power x minus k as q raised to power x by q raised to power k. So this will be equal to summation ext x minus 1 c k minus 1 p raised to power k q raised to power x by q raised to power k. Now p raised to power k and q raised to power k are constant terms, so we can take that outside of summation. So this will be p raised to power k by q raised to power k into summation e raised to power xt into x minus 1 c k minus 1 times q raised to power x. Now we can write this as p raised to power k by q raised to power k summation e p times q raised to power x into x minus 1 c k minus 1. Now see, we can take x less than q, so our value will be x is equal to k to infinity. Now if we will expand the summation, our first value of x will be k, so first value will be p raised to power k into q raised to power multiplied with e t q raised to power k into k minus 1 c k minus 1. So this will be 1 plus e t q k plus 1 into k plus 1 minus 1 k c k minus 1, and k c k minus 1 will be equal to k only, plus e t plus 2 raised to power k plus 2 minus 1, k plus 1, c k minus 1. This will be equal to k into k plus 1 by 2. Now, so if we will take et cube raised to power k common, so this will be equal to p cube k cube et cube raised to power k, and this will be 1 plus k into et cube plus k into k plus 1 by 2 into et cube raised to power 2, and so on. Now this if we will know that 1 minus x raised to power n equals to 1 plus x into n plus n into n plus 1 by 2 into x square plus n plus 2 into n plus 1 into n by 3 into 2 x cube. So this is expansion for 1 minus x raised to power n, and here our x is, this is in multiply, here our x is et cube, so and n is k, so this will be equal to p raised to power k by q raised to power k into et cube raised to power k into 1 minus et cube raised to power k. Now if we will expand this, so this will be et raised to power k and q raised to power k. So q raised to power k will be cancelled by q raised to power k. So this will be pk into etk into 1 minus e raised to power t into q raised to power k. Now one mistake is in this, that this is 1 minus x raised to power minus n. So this will be 1 minus etq raised to power minus k, and also this will be etq raised to power minus k. So this will be pet raised to power k divided by 1 minus etq raised to power k. So this is our moment generating. Now we know that our moment generating function for negative binomial distribution was pet raised to power k 1 minus qet raised to power k. Now we will try to find out mean using our mxt. As we know that mean is denoted by expectation of x, and that is equal to m dash 0. First we have to find first derivative of moment generating function, and then we will put t's value equal to 0. Now m dash will be equal to, now this is a derivative of u by v, so this is equal to u dash v minus v dash u by v square. So this will be equal to u dash for first numerator's derivative. So this will be equal to k times pet raised to power k minus 1 into pet. As we know, derivative of e raised to power x is e raised to power x into v. V is 1 minus qet raised to power k. So this is our u dash v minus v dash u. First we have to find v dash. This will be equal to k times 1 minus QET raised to power k minus 1, because we know d by dx of x raised to power n equals to n times x raised to power n minus 1. So, into derivative of what is inside the bracket. So, this will be equal to 1's derivative 0 minus QET's derivative q into ET into u. U is PE t raised to power k divided by 1 minus QET raised to power 2k. Now we have to put value of t equal to 0. So this will, every ET will be equal to a raised to power 0, and that will be 1. So this will be 1, this will be 1, this will be 1, this and this. So this will be k into p raised to power k minus 1 into p into 1 minus q. 1 minus q is p raised to power k. So this will be k p raised to power k minus 1 p 1 minus q p raised to power k minus, and this minus. So this will be plus k 1 minus q, that is p raised to power k minus 1 into q into p raised to power k divided by 1 minus q, that is p raised to power 2k. Now these three will make p raised to power 2k, and in this will make p raised to power k minus 1 into p raised to power 2k minus 1. So this will be, if we take k into p raised to power 2k minus 1 common, so this will be p plus q divided by p raised to power 2k. So this will be, as we know, p plus q equals to 1, so this will be k by p, and that is our mean for negative binomial distribution.